that. All right. You think? Okay, just let it go. Uh, Other thing I have here is labs. So some of you are taking the labs, some of you aren't. For those of you who I'm not keeping busy of enough and you need more work, there's interesting things under the labs if you want to play with those. How many people have filled out my movie survey? How many people have not? Raise your hand if you have not. You get the finger. Fill that out today. I need that data today, today, today. You got to do that today. So when we get to the lab, first thing you're going to do is fill out that movie survey. I got to have that data today so that my lab students can finish their work because we have some data collection there. Oh, shit. Oh, well. Okay, if you already did it and you didn't have your email in there, no big whoop. I got the data. If otherwise I resent the later one, that one's fine. So I just need data. All right, let's see what else. That would be sampling error, yeah. Researcher error. Okay, so we're gonna play with data. My favorite sport is soccer, and my favorite soccer team is the Portland Thorns professional female soccer team in the MLS. And so I've got some data on the Portland Thorns there. And so what we're gonna play around with is their heights. Now, it's not really a random sample, right? It's a convenience sample. Yeah, I went to their website. There was the data. I grabbed the data. They're my favorite team. I didn't bother looking at anyone else. So I thought I would grab another data set. So I like the Timbers also. So I got the Timbers data too. This would be clustered. So because I grabbed a specific team. Now it's still, there's no randomness involved there because I just picked my favorite team. So I could introduce randomness by picking a bunch of MLS teams kind of randomly. And then I would want to add additional randomness to that by only picking a subset of each group. So for example, I might do a systematic sample where I start with the third person in my list and grab every fifth. Okay, so between clustering, randomly grabbing different teams, and then within that team, randomly grabbing some individuals, then I'd be assured to have pretty good data. And so let's suppose that I'm concerned, like, what is the average height of a professional soccer player in the United States? Okay, so that's what I'm aiming at here. So I just want to play around with this data. I also sorted it by male and female. I thought that might be interesting. Is there a difference in the average height of males than females for soccer players? Well, we believe there is in regular population, so we might believe that there is in soccer players. Is that going to be a fact? We don't know till we look, right? Okay, so I'm going to play around with this data, and I'm going to use all the tools plus a little bit more that we've talked about. So the last thing we need to talk about here is the idea of deviation and variation, and we're going to work into an idea called standard deviation today. So let's write that down. So we are playing with, oops, average height of an MLS player. And one of the big goals in the immediate part of the class is going to be working our way up to the idea of standard deviation as a measure of variation. That's an R, believe it or not. Oops, I had that right the first time. Standard deviation, yikes, okay, which I usually abbreviate as STD. And this is a measure of variation or spread. What other measures of variation or spread have we talked about so far? Any thoughts? You guys got to be louder than Monday. Come on. Spread. Skewness is a way to talk about variation. Absolutely. Yep, good. Max and the min, sure, those are good ones too. Uh, Outliers are, yeah, they're involved in spread. Max and the min give us what? Range, okay. And we have another kind of range we calculated last class. It's got IQR, yeah, right on, IQR, so interquartile range. So we're going to play with all of those things right now. So deviation, I did talk about deviation in class before. Anybody remember what deviation means roughly? How far you are from the average, yeah, how far you are from the middle, right? So we're not all average. Some of us are below average, some of us are above average for all kinds of things. And deviation is your distance from that middle. So let's just ask my spreadsheet here to calculate for us the average value of the males and the females. We'll split it out in a little bit. So I can just say, I'll give a little label here, average. And then I start my formula equals average. And then I grab my data values. And sometimes you have to grab the data set by clicking and dragging. Other times you can just click on the heading for the column. And for my particular data set, the average appears to be 69.333333 inches, 69 1/3 inches. Okay. I can then use that to calculate everybody's deviation. So I'm just going to insert a column to the left here. And I'm just going to call it dev for deviation. And it's going to be equal to, now here's the deal, right? Some people are below average, some people are above average, right? So I want to get the order of the subtraction right. So if somebody is above average, like suppose somebody was 6 feet, that's a little taller than this, right? So I want to take 72 inches minus 69, and then that would show that they're about 3 inches above average, right? As opposed to someone being, say, 64 inches tall, then they would be about 5 inches below average, agreed? So I think to get the signs right, above or below, I want to do the actual measurement minus the average. That makes sense? So let's try that. So like 64 minus 69 should be a negative number, true? So I click on that cell, I click minus, I click on this cell, and then I'm ready to fill it down, right? Almost. There's one problem with my formula before I can fill it down. Yeah, I need a dollar sign. Yeah, the measurement here is going to change each time, and that's appropriate. But when I fill the formula down, it's going to change the F1 to an F2 and then an F3, and that's not where the average lives. So I need to tell the formula that the 1, the row, is fixed. And I only need to worry about the 1 because I'm copying down. I'm not copying left and right. The F's going to be fine. So once I fix that, and the dollar sign means it fixes either the row or the column depending on what you put it before. That's what's called an absolute, oh shit. That's what's called an absolute, darn. An absolute cell reference. Okay, so I can see some people, and notice I have these guys sorted by height already. And so I can see the lowest heights are here. They have the greatest deviation to the left. And then there's some people that are pretty darn close to the actual center. And then there's people with positive deviation. Okay, so some people are below and some people are above. That's a lot of numbers. Suppose I had, you know, 1 million data items and I found all of their deviations. I need to summarize their deviations somehow. Okay, so I might want to find like the average deviation, or I might want to find what do all the deviations add up to. Okay, any thoughts on what's going to happen when I try to add up the deviations? I'm going to get a very special number. Or if I average those deviations, check this out. This is awesome. Equals sum. Add up all of these deviations. What's a deviation again? Difference from the middle being average in this case as opposed to like median. And so I close my parentheses, I hit enter, and it says the sum of the deviations is 0. Because it's the middle, right? There should be equally weighted stuff on each side. Okay, so the signs are important because they tell me whether someone's below average or above average. But they're also a problem when I try to summarize the deviations. But I need to summarize the deviations to talk about spread. So I have options. What's an option for dealing with this zero sum problem? Give me the most obvious option. What's that? Just get, yeah, make the negative positive. Yeah, that's taking the absolute value. Okay, so then I can find the average value of the absolute values of the deviations, and that will give me, you know, an estimate of that. So let me write that down, because that was a crazy idea. So let's see, I said to find the mean or average of the absolute values of the deviations. Deviation, there we go. Since this is recording live to the internet, if I misspell something, could you guys correct me, please? Highlight things. Mean absolute deviation is what it's usually referred to, and in math we love acronyms, so we would call that MAD, which is a lovely acronym for a statistical term. When I see mad, I think like that's bad. And it turns out people did do this for years, and then somebody pointed out, you know, there's problems with that. It doesn't do a good job of reflecting what's going on in the population for a variety of reasons. And so someone said an alternative to just stripping the signs is what the absolute value does. Alternative. So instead of stripping, because the signs are a problem, agreed? But they're also important. Stripping them, somebody figured out, is a problem also. And I can't explain why, it's kind of weird, but someone said, well, let's square the numbers instead. Okay, let's try that. Where'd you go, numbers? There you are. All right, so let's add another column here. Insert column to the left. Yeah, there we go. And so I'm going to take the deviations and I'm going to square them. We just want to go equal, you guys squared, boom. And this is misbehaving. Let's hope it behaves at the end. All right, got that sucker. All right, so, whoa. What if I do this and bring it back? Will it behave? There we go. All right, so we have video errors going on. So I'm going to add these up. Well, I already have an add up function here, so I can just copy it over. All right, so it gives me a sum of the squares of the deviations of 500, blah, blah, blah. Now, the next step in this, it depends on whether I have a population or a sample. What was I considering this year? So I'm considering a sample, right? Because I'm looking at all MLS players. So this is a sample. It's not a good sample. It's a convenient sample, but we're going to go with it. So the rule on samples is you square all those deviations. And then Excel, to add things up, uses this symbol right here, which is pretty popular in math to add stuff up. So we add up all those squared deviations. And if you're working with a sample, now normally if I was going to do an average, I would divide by how many. With samples, you divide by how many, which we usually call n, but minus 1. Okay. And this calculation right here is what we call the standard, the variance of a sample. Variance of a sample. If I was only concerned about the timbers and the thorns and I didn't care about any other people or soccer players, then I would say it was a population. Then I would just divide by n here. And the reason I'm pointing that out is this is by hand, it's a wicked time-consuming process. On a spreadsheet, it's moderately time-consuming. So there's just buttons that we'll push later to do this. We're not going to go through all these steps all the time. That's what's called variance. To get back to the idea of deviation, I have to undo the square. How do we undo a square? We take the square root. Yeah. So new page here. So if I take the square root of the sum of those deviations squared over n minus 1, right? So I square the deviations, I add them all up, I divide by n minus 1. Then I take the square root. This is what is referred to as the standard deviation of a sample. And there's some people who did some really fancy math that involves calculus, and they proved that this version of talking about spread is much better for going from samples to populations than the mean average, the mean absolute deviation is. This is a better predictor of what's going on in populations. Standard deviation of a sample. N is the number of the number of items in the sample. Yeah. So N equals number of observations. If you find you really dig statistics and you like math, then if you take a couple more statistics classes, then you get to justify that this formula is better than the absolute value one. Okay, but it involves calculus too, which is wicked cool, but at the same time, there's a lot of people that just aren't into that kind of thing. Yes, Jory. What do I call what? The squiggle? This whole thing? Standard deviation of a sample. Without the square root, that is called variance. That is called variance. And in this class, we will almost never use the variance. We just go straight to the standard deviation. There are reasons to use the variance later on in other kinds of statistics, but we're just not going to do that kind of thing. All right, so we're just going to jump to the standard deviation. So there's different kinds of deviation. There's the deviation of an individual, just a subtraction from the mean. There's mean average or mean absolute deviation, which you can do that, but it's not a good predictor if you're trying to make assumptions about a population. It turns out this crazy calculation right here is the way to go. Okay, so do you need to memorize that formula? No, but I need you to know where it comes from. Okay, but you're never going to actually plug it in and use it. So it's in the book, you'll see it in there. All we need to know is that all modern math software has a button that says find me the standard deviation. And we just have to identify whether it's a population or a sample. Okay. So I'm just going to finish my calculation and then I'm going to check the computer's version to do it. So these guys right here are sums. I need to count my observations. Now, fortunately, I can just look and get a count. How many observations does it look like I have? 49, if there's no header. Let's see, did I have a header here? I do have a header, so that means there's really 48 observations. Okay, so that means to follow my formula here, we want to then divide that sum the computer just did by n minus 1. Okay, so let's do that next. So I can say the next one is going to be sum over parentheses n minus 1. Oops, 1, there we go. And so I just say equals this guy divided by 48 minus 1 on a good day is 47. Okay. And so what did I call this number again besides sum over n minus 1? That's called the variance. Variance. And there it goes back again. I don't know why it's been doing that lately. Crazy. It's really there. How do I get the standard deviation from the variance? Take the square root of that stuff. Okay, so there's a command for square root. If I start typing SQ, it says, hey, you want to take the positive square root of a number? I say yes. I want the number above, which is invisible right now. Enter. And it says that is 3.4353, blah, blah, blah. Okay, so STD sample. And there it's back again. So because we're doing a sample, that's it. If we were doing a population, we would just divide by n, not n minus 1. And that's some fancy math with calculus some guys did that showed that this method is better than dividing by n or using the absolute value instead. If it's just, as long as we're sure it's a sample, it's always n minus 1. Yeah, and really that doesn't even matter to us. What matters is we choose the right function in whatever program we're doing. So I calculated by hand, kind of, that the standard deviation is about 3.44-ish. Okay, let's blow that up so it's more readable. There we go. That's more readable. So next, I'm just going to ask the computer, get back here, to use its standard deviation function to see if it matches what I believe. Am I hitting the wrong button or what? Back here, where are you? Oh, there you go. All right. So I'm going to ask the computer equals ST, and then it gives me a whole bunch of options, and so I can kind of scroll through them. The first one is standard deviation. My assumption is that's a population. I would have to read the documentation. Standard error, we'll talk about that toward the end. Standard deviation of a sample treats text as zeros. I think that's probably what I want. The one above, standard deviation of an entire population. Don't want that. Standard deviation of population, treat text as zeros. Okay, so why would you want the text as zeros? Well, sometimes when we scrub data, we might comment in a line. Sometimes if somebody doesn't submit something, the database will output the word null, N-U-L-L, and we want to ignore those things. Sometimes we click use the whole column, but there's a header, we want to ignore the header. Right, so that's why those functions are there. So we want stdeva. Excel has the exact same function. So I select it, and then it says, where's your data? And I just go back to the original data set. It will do all of that other junk for me. All I have to do is say, here's my data, please tell me what the standard deviation is. And I think I have pretty close to the same number. Okay, so what's my point? When I took stats, I had to do all of this by hand, which was kind of a pain in the butt. Now we have spreadsheets and calculators where we just push a button, say, please tell me the standard deviation of these numbers. That's what we're going to do. Okay, but I thought whenever I can, I want to give you some information about what these buttons are doing. Okay, so basically what they're doing is they're saying, okay, people deviate from the middle. We're trying to estimate the middle of a population with a sample. We want to know how spread out the sample is, so we need a measurement of what's the average spread. And this is the agreed upon way to talk about average spread, standard deviation. Okay, and then we just have to be conscious, is this a population or a sample? 99% of the time, it's a sample. And we want to make sure we choose that correct formula. Okay, so the formula that we will use for standard deviation, where's my notes? Right here. Standard deviation is usually abbreviated by just the letter S. Okay, when I'm talking about a sample. And on Excel, the command is STDEVA, and then you select your data. That's for a population. That's the population one. Yeah, if we're talking about the standard deviation of a population, which we will sometimes, that is called the little Greek sigma. So that symbol right there is little Greek sigma. That means we're talking about the standard deviation of a population. And the Excel formula for that, the usual one, will be STDEVPA, and then your data. And usually there's also a P without the A. It will generally give the exact same result, but not always. It depends on whether there's text in the data mixed up. We will, 95% of the time, we will use this blue formula here. Or the black one, sorry. Highlighted now in blue. Okay, so standard deviation gives us an average measure of spread, is what it tells us again. Okay. Deviation is one way to talk about spread. All right. Let's do a few other things here. Back to my data. That is the rut Excel. I want this one. Okay. So I've calculated, where are we down here? Okay, so this is what we would call S. Earlier, I found the average, which I call X with a bar over it. Since I can't easily put a bar here, I'm just going to call it X bar. And X bar is average. Just recalculate that for fun. There's my 6.333. Anyone ever heard of a teacher talking about grading on a curve? Right. My belief is that's a misuse of statistics, and it's not a good idea. But again, we all have different opinions. I'm just going to take a look at what the curve of this data is like. And so I'm going to create a histogram. So let's highlight my data. And I could do the whole frequency chart thing, but what's this one? Google Sheets does it quicker by just going and saying, I want a chart. Shrink that down so we can see it better. And it says, oh, you want a histogram? I say yes. Okay, we can spruce it up a little bit with some titles. Portland MLS Heights. We should note that it is in inches. I do not need a legend here, right? Because there's only one set of data. Scrolling down, moving that out of the way. It shows a bucket size of 2. That seems okay. Do I have a reasonable amount of stacks? Not too many, not too few. Usually we want more than 2 and less than, like, I don't know, 12 or 15. More than 6, sorry. 6 or more, there we go. And less than 12 to 15. So that would be okay. I could play around with other bucket sizes, like, I don't know, I'm very fond of the number 5. That seems too grouped together, too few stacks. 3. Interesting. Let's go back to 2. That looks slightly different than the one they gave. No, that's the same one, I guess. Okay. Let's see. Omit delimiters. I like unclicking that button because I think those little separators are cute. Horizontal title. What should I title the horizontal axis? Height in inches, maybe? Okay, and then I can switch to the vertical axis. What should I call the vertical axis? Frequency, yep. Or count. Sometimes I call it count because it's easier to spell. Frequency. All right. This is starting to shape up pretty nice. Insert it. Where'd you go? Must be up top somewhere. Ah, there she is. Okay, so there it is. Just to clarify what some things mean here, is 66 in the left stack or the right stack? The right stack? Okay, so you think then what this interval means, like this one right here, oops, is 64 to 65. Let's see, since this is being recorded, I better copy this over to my screen. New page, paste. Come on, doesn't want to paste. Let's try that again. All right, what'd you say, David? I missed that. That is true, it will be. All right, so let's just double check what's going on here. So you always need to know, how does your particular program do it? So their claim here is that there's 8 items in this region right here. So if I look at the first 8 items, there we go, or is that 9? Well, there's probably 9 because 10's right there, 9. And 9 items up to 65, yeah, so 65 is in the next column. Okay, so we always need to know what our particular software does, and not all software behaves the same. I think Excel does it the same way, but the TI does not. If you ever use your TI for data, it takes the right number and puts that in the interval. So our intervals look like this. Oh, I keep forgetting I have to write digitally here. Magic pen, where'd you go? Ah, thank you, sir. So this pen, there we go. This interval right there means that the x values that we're talking about, height in inches, they are less than the right boundary 66, but they are less than or equal to the left boundary 64. So we always need to know, is the lower bound in the interval or is it the upper bound? Because again, spreadsheet programs don't always label these the way you would like. Okay. So if I were making a frequency table here, and I was writing down my bins like human readable, I would say the first bin is 64 to 65. I would say the next bin is 66 to 67. And I want to design those bins in such a way that the maxes are always the same distance apart as I move down, and the mins are always the same distance apart as I move down. I wouldn't want to later do something like go from 76 to 79. Right? Why would that be a problem? Having that bin, is that a problem or is that okay? It's a different size, right? And so that distorts the frequency distribution. Okay, so this would be bad right there. We don't want to do that. And there was a homework problem. 2 people caught the error in the data. It was the one about AIDS patients, version A and version B. The second researcher mislabeled his frequency table. So they had one group was bigger than all the others. So we really want to be careful that we need to be consistent when we design these. All of these guys have to be the same width when we make them. All right, so what did we find the mean to be? 69.33333-ish, right? So there's 68, there's 70. So our mean lives about right here. The mean is called X with a bar over it. What was our standard deviation? 3 point something? 3.4-ish. Usually, anybody remember the rule on rounding these guys? You take it one more place than the data was. So since my data is height in whole number inches, then any calculations I do, I should round to the nearest tenth, is the rule. If somebody measured themselves as 75.5, then I would have to take my mean and standard deviation to the nearest hundredth. Okay, always one more than the data. So let's clean that up. And then what we do next is we use the standard deviation to talk about how spread out the data is in the following way. What we do is we put the mean in the middle, X bar, and then we say, what happens if we look one standard deviation to the right? So that would be taking X bar and adding S to it. And we also want to say, what happens if we look one standard deviation to the left? That would mean take X bar and subtract S from it. Okay? So X bar is equal to this number. If I go one to the right, that will be equal to this plus that. So if somebody has a height of 72.8 inches, they are exactly one standard deviation to the right of the middle being the average here. We can go the other way and say, let's take X bar and subtract that from it. Okay, so there's nothing special about being one standard deviation above the mean. You could be 2 standard deviations above the mean, or 3 standard deviations above the mean, or really tall and be 4 standard deviations above the mean. So it's common to do the first 3 standard deviations on each side to talk about spread of data. So we are then going to find X bar plus 2S and X bar plus 3S. X bar plus 2S and X bar plus 3S. So then I just keep building this out. Plus 2 of these guys. Similarly, we'll get that plus 3 of these guys. So we use the standard deviation as a ruler. And we talk about how many standard deviations is somebody away from the middle. Okay, so it's kind of similar to talking about quartiles. Are you in the first quarter or the second quarter or the third quarter? Okay, standard deviations above and below the mean are a same idea. They're a way of kind of ranking data. So it's a different kind of rank. And let's see, I am running out of room. Let's move those over. Oh, crap, too far. Oh, Jesus, excuse me. Stop. Okay, that should be far enough. Sorry about the antics there. X bar minus 2S I need to find, and I also want to find X bar minus 3S. And this is, again, another place where a spreadsheet is super handy because it's a little more work doing it by hand. So please make a note of these numbers as I calculate them. Minus 2S. And then the mean minus 3 S's. Okay. So we always want to take a look at which data points are 2 standard deviations to the right or 3 standard deviations to the left. Sometimes we'll also count how many of the numbers are within 1 standard deviation of the mean. How many of the numbers are within 2 standard deviations of the mean. Those are other things we'll take a look at. That's a lot like looking at quartiles and the interquartile range. All right, we got those numbers down. Oop, my spreadsheet is freaking out. Can't quite see them all. Come on. How annoying. Okay, so there's all the numbers. You got them down? Write them down. You can't see them? Oh, shit. No, just those numbers right there. All right, so we have 59, 62.5, 65.9, 69.3, and so on. I'm going to steal those and copy them into my sheet here. Okay, so there are my numbers. Let's put them down here. So I'm just going to mark them off on my chart here. Magic pen. Color red should be good. All right, so here I've marked my middle. One standard deviation to the right is, where'd it go? X bar 72.8. So 72.8 is going to be right about here. Then 76.2 is going to be right about here. That's 2 standard deviations to the right. And then 3 standard deviations would be 79.2, which I'm guessing is about right here. Notice they, to the best of my artistic ability, those guys are equally spaced. How far apart are those two measurements? 3.4-ish. Yeah, so that's what we call S. They are S apart. S here is approximately 3.4. Yeah, so basically I'm saying start at the mean, then go 3.4 to the right, go 3.4 to the right again, go 3.4 to the right again. Okay. So I've now shown 1, 2, 3 standard deviations to the right. We'll go the other way too. So X bar minus S is 65.9, pretty darn close to 66. That's about right there. Oops, a little off. Oh well, 62.5 would be about here, I think. And then 59 would be way back here somewhere. Okay, so just some rules about data. So I'm just going to make a little chart within blank STDs of mean versus percent. So if data is what we call normally distributed, that's the idea of a bell curve, then within 1 standard deviation, I expect to find about 68% of the data. Okay. So for us, that would be between 65.9 and 72.8. Okay. So in this region right here, I would expect to find about 68% of the data. Within 2 standard deviations of the mean, we expect to find about 95% of the data. And within 3 standard deviations, it depends on who you ask. For simplicity, I'm going to call it 99%. It's actually a little higher than that. I would expect to find 99%. Now, I prefaced, this is only true under certain conditions. What, did anybody hear the condition I mentioned? I said it too fast. If I believe the data is what we call normally distributed. So again, if, big if, data is normally distributed. Problem, not all data is normally distributed. Most measurements about people and a lot of measurements in nature tend to be normally distributed. Normally distributed means they fit this kind of description right there. It's called a bell curve. Okay, so normally distributed means the data has a bell curve. There are different kinds of bells. When we talk about the bell curve, we're talking of what's referred to as a normal curve. We'll define a normal curve more carefully later in the quarter. Okay. But this is just kind of a rule of thumb that goes on. So most of the time, I'm going to expect within most, would you agree, if data is normally distributed, then most of my data should be within 2 standard deviations. most being 95%. That's a heck of a lot of the data. Okay. There are other rules too. There's a guy named Chebyshev who came up with a slightly different rule for data that's not necessarily normal. So I'll show you his rule. I can spell his name right. Chebyshev. So Chebyshev's rule is kind of like the normal rule. It refers to standard deviations from the mean, so STDs from X bar versus percentages. And Chebyshev's rule doesn't say anything about one standard deviation, but it does talk about 2 standard deviations and 3 and so on. And let's see, I gotta remember this. I believe it's 75%. His rule goes like this. If you have k standard deviations, then look at the fraction 1 minus 1 over k squared. Okay. So if k were 2, I would have 1 minus 1 over 2 squared. What's 2 squared? 4. So 1 minus a fourth? 3/4. Okay. So Chebyshev's rule says that about 3/4 of the data should be within 2 standard deviations of the mean. Okay. If we went 3 standard deviations from the mean, 1 over 3 squared, that's 1/9. That would leave me with how many ninths behind? 8/9, correct? 8/9 as a decimal is 0.8 repeating forever and ever. So I could, if I wanted to round to the nearest whole percentage, I could say it's like 89%. So Chebyshev's rule says about 89% should be within 2 standard deviations. Okay. So this is regardless of distribution. Okay. So a histogram is a distribution. Okay. So if we look at our distribution, we ask ourselves, does the distribution look kind of bell-shaped? I don't see a bell there. Do you? The heights are pretty much clumped up in the 64 to 70 range, and then it starts to kind of drop after that. You might argue there's a tail to the right because it's got that little bit of tall guys, I guess, that play soccer. Again, this is men and women, right? So we have a mixed population there. So is it safe to say that this is normally distributed? I'm going to say this doesn't look normally distributed to me. The other way you test to see if something might be normally distributed, and again, it's a might, is does your data fit these percentages? Well, we can pretty much count and see that here. It's not a big deal. So let's see. Within 2 standard deviations, I'm hoping to see about 68%. So I go back to my data, and I'm going to have to shrink it down to see this. Okay, what is, again, 1 standard deviation to the left? What was that number? What was it? I didn't hear that. 65.9 is 1 standard deviation to the left? Okay. So 65.9. So this number is bigger than 69.5. What was 1 standard deviation to the right? 72.8. Okay, so scrolling down till I see something. So all the way up to, okay, so that's right to here. Oh. So all the numbers from 66 up to 72, oops, I missed one, are within 1 standard deviation of the middle, according to our calculations, the average. How many cells did I highlight there? Let's see, from 39 back to 11. So that's 29 cells I just highlighted there. Okay, 29 out of how many? How many people? 48? Okay, so let's see, what is 29 out of 48? 60%. 60% of our data is within 1 standard deviation of the mean. Is that close to 68? Depends on what you mean by close. Okay, I would say no, it's not really that close. So that's what I would call. I'm just going to say x plus/minus 1s. Okay, I mean x bar there. Let's take a look at the x bar plus or minus 2 s's. What was our number for 2 standard deviations below? Okay, so everything's above that, right? And then what was our second standard deviation above? 76.2, okay. Okay, so 76 is less than 76.2, right? Okay, so how much of our data is within 2 standard deviations? Oh, it looks like all of it. Let's check that out. So here's 2 standard deviations to the right. Let's use the highlighter right here. Here's 2 standard deviations to the left. The tallest people I have are 76 inches. So they have to be they are at the very beginning of this last clump there. All of my data is within 2 standard deviations of the mean. Okay. What if it was normal? What was I hoping for again? 95%. Okay. So does this fit the idea of being normal? Okay, so let's see. This is equal to 100%. I'll just call it 1. I would say no for 2 reasons. 1, it doesn't look like a bell. Doesn't look like a bell. 2, 60 is not, I don't think, reasonably close to 68. And 100% is significantly more than 95%. Okay. If that were the number for 3 standard deviations, I would have been okay with it. 99 versus 100%, I would have been okay, but I think it's a little too far. So I would say these guys are not normally distributed. Now, it is believed that heights of human beings in general are normally distributed. Okay. Which means if I get a random collection of people and I get enough of them and I graph them, I should see a bell shape. I should see about 68% of those people are within 1 standard deviation, 95 within 2 standard deviations, and 99 within 3. Okay. So the question is, how many people do I need to make it look right? Okay. So what does it appear? It appears soccer players' heights are relatively uniform. They're kind of tightly packed together. There's not people that are too tall or too short. They're all kind of sort of close to the same size, although there's a few tall people.
Like population-wise, wouldn't it always be zero sum anyway? If you took a whole population, it would always be bell curve, wouldn't it?
No, there are some populations that are skewed for some reason, but well, there's all different shapes you can have when you make a histogram. So that's yeah, it depends on how outliers are. So I'm trying to think of an example of something I know for sure that's skewed. Gosh, I'll have to get back to you for that. Let me write a note about that. Skewed examples in nature. So one problem is there's a lot of people make a lot of assumptions about normal distributions and they use those percentages kind of willy-nilly, and it's really not safe to do so. You have to kind of justify that you have the right to use them. And here I'm thinking I just don't have the right to say I should use those percentages. Okay. Now Chevyshev's rule is a little looser. It says it's more like an at most thing, or it's an about thing. So I have within 2 standard deviations 100%. Chevyshev says you should have at least 75%. Yeah, I got at least 75%. So it's much looser about what you should expect to find. Just for fun, let's check out another data set. Back on here. Let's see. Somewhere I have your heights. Where did I put that? Right here, I think. Okay, so there's your heights. I don't remember, did we make a histogram for that in class? Is that what these are here? I didn't label them. I hate when that happens. All right, so let's grab your heights and just make a fresh one. Make a chart. So I guess we did before. Does that look like a bell curve? No, does not. Okay. Heights are usually normally distributed. It just means maybe I don't have a good sample. Somehow statistics students lead to weird, not normal distributions in height. I don't know. Let's check another one out. What other data did I collect from y'all? That's everybody bunched together. I don't have a way to segregate this data from Hermiston and Pendleton because I didn't ask that information. I would have to resurvey to get that. I could do it male versus female. It could be the males are making this all messed up, and if I did the females, then it would look normal, right? So I could sort by female and then redo it. I think I asked your pulse rates, right? Where is that? I thought that was in this data set. Oh, there it is. Okay, let's check out pulse rates. Pulse rates are ones that, like temperature also, of average temperature of a person, that's believed to be normally distributed too, based on studies done. Let's check this chart. That looks a little more normal. Okay, these look like they're stuck together. That's just an artifact of the way I'm blowing things up. If I shrink it down, they might separate. Barely. That's a little more bell-shaped. Actually looks more like it's giving me the finger. Okay, so you can't assume normal distribution even if it's believed for the population because every sample is different. You have to do a bunch of small samples that have some randomness to the way individual was assigned to each group, and then do a bunch of histograms and then check those percentages out to kind of test that out. Let's see. Do I have any other data to test? Okay, so I think that's it for now. So I just got to look back at my notes. What else did I need to talk about? Yeah. So I mentioned this verbally, but I didn't write it down, and I want to do so now. Data, Portland Thorns, okay. So let's see, 65.9, that's pretty darn close to 66, right? Okay, so 66 is about 1 standard deviation below the mean. Okay, if I look at the roster, there were a couple of people that were 66 inches in height. Okay, so they are almost exactly 1 standard deviation below the mean. And earlier I mentioned we can use standard deviations as a measuring stick. So I just want to make a note of that, and then we're going to head over to the lab to play. So STD as a measuring stick. So in other words, how many standard deviations is a particular score from the mean? Okay, so I'm just going to hypothesize here. So I've played soccer in the past. I coach kids soccer sometimes. I can kick a ball and sometimes it goes in the goal. Okay, now it either goes in or it doesn't, right? So you might argue wrongly that I have a 50% chance of getting it in. That's a pretty good rate. So I say, hey, I'm going out for the Timbers, right? And so they look at my height and they say, okay, you are 68 inches tall. Does that fit with the heights we think soccer players should be? Yeah, I'm in there, right? So we could calculate how many standard deviations am I from the mean. So to do that, I have to first find my deviation. So deviation is where you take your score and you subtract the mean, 69 1/3. And so I am what? Negative 1.3 below the mean, or 1 1/3, I'll call it. Negative 1 1/3 below average. That's my deviation. To convert that to standard deviations, you just divide by the standard deviation. So my standard deviation was about 3.4. Okay, so then I whip out my computer and I do that calculation. Let's use a new tab. So let's see, 1 1/3, that would be 4/3. I could just call it 0.3. Let's round, what the heck. So negative 1.3-ish divided by 3.4-ish gives me, oh, it's not available. It flashed there for a second. What was it, like 0.38-ish? Come on, give me a number. Didn't match anything. You son of a gun. Let's get rid of the negative. Thank you very much. Okay, so about negative 0.38. So where'd my notes go? So that calculation right there is approximately negative 0.38. So what does that say? That tells me that I am about a third of a standard deviation below average. Okay, it's not 0.3, it's close to a third, right? So 68 inches, my height, is about 0.38 STDs below average. And the idea of using a standard deviation as a measuring stick, that's referred to as a z-score. And z-scores are very popular in statistics. We'll use them later on in the course. That's a z-score, when you use the standard deviation as a measuring stick. Okay? All right, so I think I should shut up now. So what we're gonna do is we're gonna go to the lab. I'm gonna post a link to a spreadsheet of, let's see, we could either play with height some more or pulse rates. Let's play with pulse rates. I'll post some pulse rate data. So that'll be, I'll put it on our little blog. And what's the first thing you're gonna go to the lab if you haven't done so already? Do that movie survey, please. Yes, thank you very much. Okay. So M20 is where we're headed.